Thanks a lot. For sure everybody here lives in a different bubble. And in my data science bubble, everybody is talking about vector search or using vector representations literally for anything. And today, if you haven't heard about that, I would like to convince you to start using them just because they offer some cool properties that we haven't seen before. But first of all, we need to focus on the way how we implement search engines nowadays. If we have a particular search query and we would like to find some documents which are relevant for that query, we would probably need to perform some kind of normalization. So we'll convert all the words into their root forms. We'll remove some words which are meaningless, so-called stop words. We would probably replace some synonyms just in order to bring all the queries into a normalized form. So there is just a limited subset of all the words from a particular language. Sometimes we could also try to fix some typos, just because our methods strongly rely on the words that are used in a query. So our original query, after all this preprocessing, could look like this. So some of the words, those the, of, in, would be completely removed, and some others will be converted into the basic form. And this is actually the process that we currently do. If you work with Elasticsearch or any different engine, then you probably use BM25. This is the most commonly used algorithm for textual search. And this is under the hood based on a simple back of words model with some extensions. There is a special formula of how to calculate the relevancy score of each document. And this is actually using some variation of TF-IDF, so we have some different values for words which are not, which do not occur that often. And this is typical. We try to promote those words just because we believe that they should capture some more important pieces of information. So in this process, every document from our corpus receives some kind of score, no matter how we calculate it, and then we just select top 10 results based on this score, so the highest entries will win. But there are some facts about BM25. Well, every single permutation of query would have the same representation just because the words are the same. So as a result, it doesn't really matter how we perform this query, because it will be based on the single words that are used under the hood. Word synonyms won't be recognized at all unless we provide a mapping of words into some different ones, just because we only rely on those exact words. So there is no semantic search included in BM25. And we need a lot of heuristics just in order to start working with that, like lemmatization or stemming. So there are a lot of things that we need to perform manually, and that's a process that requires a lot of effort. And surprisingly, if we wanted to put this original query, we could probably not receive the results which are obviously relevant just because the words are different. So we all know that story, right? It's a pretty old fairy tale, and I assume that it was not written in the same words like we would use nowadays. So if you are interested in having some risks of food delivery, then the system that would be based on BM25 won't ever recognize this particular story that is definitely relevant in some way. So this is a huge drawback of BM25 search, this old method that we currently use. And actually BM25 is based on inverted index structure that is quite commonly used, and it dates back to 15th century, if I remember correctly. But there are also some other methods which do not require providing all those manual processes, all those heuristics, and that can solve the issues that we have with textual search almost effortlessly. And those methods are purely based on neural networks, deep neural models. Just as a reminder, this is like a basic structure of the neural network and how it works under the hood. So basically, a neural network takes some kind of input. It might be an image or text. And in the simplest case, in case of classification, it provides us a vector, which might be thought as some kind of probability distribution over different classes. In this case, the position corresponding to flower gets the highest result just because that was presented on an image, right? And that's, in a nutshell, the structure of the neural network. However, if we decide to cut off the last layer, this last layer is typically using some kind of softmax activation function just to convert those numbers into the probability distribution. So if we just cut it off, it turns out that the last layer, the previous layer, also contains some useful pieces of information. This is just a different representation of the original data, which is actually which is not that easy to be interpreted. So to say, it's impossible to interpret those values just by having a quick look. So that's an issue, but still it represents the original signal that is present in the data. So we can try to compare those signals, compare those different representations. And that's basically this vector, which is being produced by such a network right now, is called encoding or embedding, or it used to be called distributed representation back in the days. But embeddings are quite commonly known actually for anybody working with deep learning models, I assume. And that may remind you of something, because this is, in a nutshell, a numerical vector, no matter the dimensionality of that vector. But this is basically some kind of vector of coordinates in a specific space. In the simplest form, you could take like a position of the city, and this is also like two-dimensional vector representing a particular point in space. But that's also true for some higher dimensional vectors, like 1,000 dimensions, would also encode a specific point. And the assumption of vector search is that two pieces of text, or two examples, two different images, which are similar in some way, should be also closed in the latent space they are converted into by our deep learning model. And that's actually true. And if we take just some existing networks and try to perform that process, it seems to be working fine. Or we can also train our networks in a way that they will produce those embeddings to be close to each other. And that's, in a nutshell, the main idea behind the vector search. So those neural embeddings represents data in n-dimensional space, what makes easy to compare those points, compare those examples to each other. Because as an input, we could take some text of a different length, and that might be an issue if we wanted to compare them against each other. Now, with a fixed representation, it's way easier. And we can use some commonly known distance function to do that, like Euclidean distance or dot product or cosine distance, and cosine is probably the most popular one. And the assumption is points which are close to each other represent some similar objects in some way. And that's basically it. So now, if we wanted to find some relevant documents to a given query, we would no longer need to provide some synonyms, just because our model should be trained in a way that would encode those two queries in a similar way. Not exactly the same, that won't be possible probably, but still there shouldn't be huge differences between those vectors, just because they represent actually the same query. We use different words, but the original idea behind these queries is completely the same. So that would be kept by a properly trained neural model. So there are actually a lot of pre-trained models available, for example, at Hugging Face datasets repository. So you can actually take an existing model and use it just right away, just out of the box. And they are typically based on some masked language models, where context defines the meaning of a word. Those are typically BERT-based models, so there are a lot of Herbert models and etc. Actually, if you have any specific domain, any specific language, maybe not any specific language, but for the most popular languages, you could probably easily find an existing network that should be capable of encoding the sentences for that language. So as a result, we should be now able to encode those sentences which have exactly the same meaning in the corporate emails to some similar representations. As you may see, those numbers in those vectors are quite similar to each other at every corresponding position, but not exactly the same. But if we just wanted to calculate the distance between those two coordinates, it should be relatively small. And that's the whole idea. So those two messages should also have a similar representation, but still different to the previous example, because they represent a different idea, some different thoughts of the original author of those texts. But there are also some problems with neural search, with vector search. There are like two ways how we call it. We need lots of data to do that. If we just want to train our own model, we would probably need to provide lots of examples. Like, for example, BERT was trained on whole Wikipedia and Google book corpus. That's over 3.3 billions of words. So that's a huge amount. And that definitely also needs a lot of time and power to train those models. And that of course, means a lot of costs, a lot of money that we need to pay for the whole training. In this case, BERT was trained using 64 TPUs in more than 4 days. So that's definitely not something that smaller and medium-sized companies could afford. So there is a different way of how we could use that. Because, as I already said, there are a lot of pre-trained models for most of the languages that you could probably work with. We can try to take an existing model with already set weights. We typically need to do it just because these original models are trained on some general corpuses like Wikipedia, for example. They work pretty well in some general cases, but if you work in a specific domain, let's say you have some medical text, then there is not that much of that expert domain included in the corpuses. So we typically need to perform some kind of fine-tuning. And by fine-tuning, I mean adjusting the weights in the network, in the original network, a bit, just so it encodes your area a little better than the original network. And similarity learning is a related concept. Similarity learning is actually a way of how to fine-tune those models so they can capture those specific domains. And that applies not only to text, but if you have some images, some videos or audio signals, actually any different type of data you can imagine that can be pushed through a neural encoder, then it might be also simply used to perform search. So that enables a lot of opportunities different than textual search, because that was the only way how we could search in a particular data set in the past. Right now, we are able to perform reverse image search. If you use Google Lens, you can do it. But the method that is in the heart of those systems strongly relies on neural embeddings, because they are also able to capture the meaning of the image as well as text if we just use a different model. So BM25 and TF-IDF won't obviously work in case of images or a different data type, so they cannot be simply used. So that was the limit. We couldn't go beyond text for search. Right now, with neural search, with vector search, it's still possible. But let me just focus on similarity learning for a while. Similarity learning is just a different way of how we train our networks, just a different type of challenge we try to solve with them. Coming back to the network structure, if you have a pre-trained model and just remove the last layer of that model, you can use those signals. So this last hidden layer would produce those neural embeddings in that case. But if you want to fine-tune them, there is still a challenge if you wanted to make this for a whole network, because it has a few millions or billions of parameters, and that cannot be done that easily. So this has been already mentioned, but there is also a different strategy of how we could perform this fine-tuning, because as a rule of thumb, we assume that those original embeddings just work well in general case. Let's say if that was trained on Wikipedia, then probably it can capture some regularities and just need some small adjustments in those areas where we want to work with those models. There is a different way of how to improve the predictions, how to improve those embeddings. We can attach a new head, and this new head might be just a simple single neural layer added at the very end of that network that will take the original embedding produced by this neural encoder and just process it through a simple step. So those original embeddings will be just adjusted a little bit from the original ones, but not fully changed. We don't want to perform a catastrophic forgetting here. We just want to make some smaller changes, some small changes in those vectors, in those original vectors produced by our network, and that's it. And the good thing about that setup, because actually I just added some new layers, right? So that would mean that there is some more weights in the whole network. But if we just focus on this setup, we could simply freeze this original neural encoder and train only the very last layer, the newly attached layer that we added to it. So that reduces a lot the time that we have to spend on the whole training. That also means that we don't really need to provide millions of examples, but in reality we can just focus on just a few thousand of well-labeled examples, and that should be enough to perform this adjustment in our domain. So this is fairly easy to be done. Well, millions of examples would require a team of people working for a few months probably, or even few years to be labeled properly. With 1,000 or 2,000 of examples, you can simply do it on your own within 2 or 3 days. So that's really easy. And with similarity learning, we no longer provide labels. In case of classification, we were providing some labels, so that was a flower. But if we want to produce some embeddings, some neural embeddings, we cannot really say that this is the best embedding for that specific image, right? That's impossible to be done. If we knew the perfect embedding for every single case, then that would be already solved. But we want the network to find those. So instead of providing labels, we need to provide some samples, and there are 2 ways of how to do it. And the first way is pretty simple. We can provide some groups. So those groups should represent objects that are in some way similar to each other. So they either represent the same class or some objects which, for any reason, should be converted into a similar vector representation. And as you may already see, if you have a classification data set, then you already have a similarity learning data set, because there is no difference here. And if you use a similarity learning pipeline, there are some specific loss functions that would take those images or those examples and convert them into triplets, for example. So let's say one of those flowers should be close to every single flower from every single object from the same group, and far away from those other examples belonging to different classes. And that's the simplest idea, and that will be handled automatically. So if you have a classification data set, that's very easy to just start doing the similarity learning as well. But there is also a different approach. So we can provide pairs of examples. That's way more complicated, because that assumes there is a process that can provide you with some similarity scores for every single pair of examples. That might be tricky. Actually, I cannot really recall a specific case where there would be an obvious choice for that. Typically, we use some kind of proxy to do it. But let's say we have some list of movies you watched, and we know that 2 movies might be similar to each other because you rated them 10 out of 10, and some different ones shouldn't be that close because you've chosen some different numbers, let's say 7 out of 10 and 10 out of 10. So the similarity of those 2 should be probably lower. And that's another approach of how to do it. But of course, most of us will probably work with Python. So I strongly encourage you, if you wanted to start doing that under those boundaries, because similarity learning is not only about attaching a new layer and performing a training on the last layer. We could, of course, do a whole retraining of the whole model, but that will require lots of time. But if you agree to those boundaries and would like to experiment quickly, I encourage you to have a look at Quaterion, which is a PyTorch Lightning compatible framework that is specifically done for similarity learning. That was developed by the company that I work for, Quadrant, but this is fully open source and already has a caching mechanism. One thing I forgot to mention that's quite important, because if you decide to freeze this original neural encoder, then there is no need to perform this encoding more than once. You can just process all your training examples through this neural encoder once, store those results somewhere, and then fine-tune this new head without doing this possibly long training, like taking all the examples from a disk, processing them through the network. You do it once, and then you can just fine-tune this single layer only. So it is possible now to perform some caching, right? Because that could be automatically handled by the framework. So this is already built in Quaterion. You can actually take your example, create your pipeline in the same way like you would do with PyTorch Lightning, and this caching mechanism might be configured so then your examples will be just encoded once and pushed to the device you perform the training on, either CPU or GPU, and then that allows to speed up the training process by 100 of times. So right now you are able to perform some experiments within minutes, not hours. Well, you would probably miss some hours spent on sipping coffee in the office kitchen, but right now you can perform a few experiments a day, compare them with each other, and just choose the best model possible. And that might be done with just a few examples. 1,000 or 2 should be enough as a starting point, let's say. There are also some loss functions already built in. So if you want to test different ones, it's possible. The implementations are there, so there is no need to provide your own. There is quite an interesting concept of skip connection head. If you worked with ResNet, you probably know that, but basically that allows to mitigate the risk of catastrophic forgetting. But there are also many more improvements over the pipeline that you would probably need to implement on your own using PyTorch or PyTorch Lightning. So if you want to perform that process, I really encourage you to go to our website and check this out. And similarity learning solves not only a semantic search. That's one of the possible challenges that might be solved with similarity learning, but there are many more, like anomaly detection. Because at the end of the day, the goal of similarity learning is to produce those embeddings, and those embeddings will be then compared to each other. So there will be some kind of distance calculated between every single pair of objects, and that might be simply used to perform anomaly detection. If the distance is relatively higher than for all the other objects, that may mean that there is a problem with a specific object. This might be thought as some kind of anomaly. But that might be also used for recommendation systems, because we could represent our users as vectors. That's also possible, and compare those users, so we will perform the recommendation based on the content that is being watched by 2 different people. We can also perform classification. Simply, if we just produce the embedding, we can find, let's say, 100 of closest examples to this embedding, and then by simple voting, we can produce the label for that. And that also means that we can provide, we can perform extreme classification as well, or add some classes almost in the runtime of the model, because still, it won't be required to perform the whole training once again, because we won't be changing the one-hot encodings of those objects, but instead we can just assign some new labels, and then by using nearest neighbors search, we can provide new labels without doing the retraining at all. That also solves question answering, passage retrieval, and many more. Actually, it's quite universal methods to solve almost literally any kind of problem. We just need to change a way of how we think of doing that. And in a nutshell, it's mostly based on k-nearest neighbors, the algorithm that you probably all know, because that is being taught on primer data science classes. And there was a problem with k-nearest neighbors just because it doesn't scale well. It works pretty well if you have hundreds of examples, because we can simply compare the distance to every single object in our database. But it doesn't scale that well if we have, let's say, thousands or hundreds of thousands of examples, because comparing the distance to every single object in the database becomes simply a bottleneck of that system. That has been solved recently. There has been a lot of going on in terms of approximate nearest neighbors. So this is a set of methods that allows to perform this nearest lookup way faster than before. And of course, you don't really need to implement that on your own. There are already some existing tools that you can use, and that performs the nearest neighbor search within a few seconds, even for millions of objects, just because it is based on some specific data structures that simplifies the lookup for the closest entries. And Quadrant, an open source company that I worked for, is one of the solutions here. This is a vector search database that allows to perform this nearest neighbors using HNSW algorithm, which is a graph-based data structure based on proximity of objects. And that performs an approximate nearest neighbor search. So, in a nutshell, it's written in Rust, what makes it really performant. There's an HTTP and gRPC protocols available. You can run it in a distributed mode. You can also provide some different examples. That's also important, because vector search is not the only thing that we want to do at the end of the day, because some vectors might be similar to each other, but we may also have some other criteria that should be fulfilled. Let's imagine we want to find some similar, we want to find a specific piece of cloth. We have a photo of that, and we can just calculate the embedding and compare with our database of embeddings. That's pretty simple. But let's say we want a specific fabric. We want a specific color of that. We need to apply some additional filters on top of vector search, and that's also doable. Actually, every single vector database provides this kind of feature. Quadrant is a little bit different to the rest of the engines, just because this is already incorporated in vector search phase, what makes it quite performant. And if you have other questions, I would be happy to answer them. If not, here are my social media and QR code links to the Quadrant website. Thank you very much.
Thank you, Kacper. I really like your snippets from Office emails. But any questions related to vector search from the audience? One question there.
Hi, thank you for the presentation, and my question is, what is the importance of the speed and generally the performance of building an index to a vector search? So you mentioned this, one algorithm at the end that is used for vector search for the approximate nearest neighbors, and I wonder if actually building, I suppose it builds some form of an index for search. How important it is to actually do it in a fast manner.
Yeah, basically, building this index is not a bottleneck of those systems, just because if you have all your embeddings already computed, then it's fairly easy, and just by looking at the benchmarks we did, you can index like 1 million of points within a few minutes. So that's not an issue. The issue here is when you want to change your model. You created a new version of your neural encoder and just want to change those embeddings you have in the system. That's the huge issue, just because you need to recompute all the embeddings that are stored right now in your database. You need to recompute them and store them again. And storing them won't be an issue. The issue will occur if you want to perform this vectorization, just because putting like millions of objects through a neural model will take days or even more. So that's the whole issue. But indexing those points, it's not a problem at all. It takes a few seconds for a few thousand of examples, and this is split into segments. So we don't necessarily build like a huge structure that will contain all of them, but this is split into segments. So those are typically smaller and allows to perform some concurrent reads when we perform the search. So this is quite performant, I would say. That's not an issue.
Unfortunately, the time is over, so if you still have questions to Kacper, I think he will be around. So please let us thank Kacper once again. And